Any questions before we begin?
Do you have any questions there? No.
How you doing, Lena?
Doing
Your
good.
stuff will be graded eventually. I am behind on my grading. Can I just say how oppressive grading is?
I
It's the
can
worst
imagine.
thing known to humanity. Teaching is the greatest. Grading is the worst. It's like it balances out to like I'm an okay life. So Zach, what lights do you have behind your whatever that is? Exactly what is that?
I don't know what they're just called like rope lights, and I got them with my dad at like Costco like over the summer. But there's like a remote where I can change the colors.
No, you don't have to change it. Oh, is that
Yeah.
behind your shutters or something?
No. So I have it like, I think I can show it, but I have it like bordering my room. So it's like going all around the length of it.
Wow.
So it's just running up from like the power outlet up.
It looks like there's lights behind blinds, and that's what I've always thought. And I've always wanted to ask you, what the hell is that? So, what's behind you? You got a window behind you, Julia. Is it nice outside?
It's sunny.
It is sunny. It's going to be nice for the next couple of weeks. We're in a above normal temperature, so enjoy the weather as we get forward into time. So you got the PGA Superstore. Is that the one right next to Benny's, or is that the one over by Portillo's, Tim?
I think it's by more towards Portillo's.
Yeah, okay. I
think
drove
it's
by
further
that
down Butterfield Road.
Yeah, that's cool. How's Tiger doing?
Better.
So I was reading some articles saying that they think maybe he fell asleep at the wheel. These experts in crashes said it looks like it wasn't necessarily speeding as much as it was going over the curve without.
Yeah. I haven't really read into that, but I wouldn't be surprised.
Well, either way, at least he's alive, right?
Yeah.
Okay, so we were talking about the lab. So what I'm going to do today is I'm going to start, whoops. I suppose I should share my screen first. Throw you over there. Every time I throw you over there, I need to make the windows larger. Got my glasses on because you're so far away, you're blurry to me. And now I do this. Can you all see this? So a parcel.
It's just dark. Okay.
You see that. So a parcel is always this, right? It's always dry adiabatic to a point, and then wet adiabatic, boom. Wet adiabatic beyond that. And the wet adiabat's always curved like that, right? Because the wet adiabatic lapse rate is always a function of how much water vapor. It's dependent upon the temperature change and the change where that temperature change takes place. Where they switch over is the LCL. The parcel is always in blue. The environment is always in red. So what I could do is I could put an environment in here that looks something like this. Okay. And then above that point, it might be something like this. So if that's the case, what is this? What's that going to be, guys?
That be the EL?
No. What's this point?
LCF.
No, the other way around.
LC.
What's this point? Right, that's the equilibrium level. So what color were we shading Cape in? Was it purple?
Is that the spot like tropopause?
Hold on a sec. Hold your thought, because I want to affirm you.
Oh, we shaded it as orange, and NBE we shaded it as purple.
Well, whatever. I don't know what color it should be. It doesn't really matter. But in this case, obviously, this is this is PBE or CAPE. This is NBE or what? What else could we call it? What's another name for NBE?
Sin.
Sin. Sometimes you may see sin with an H. I don't know. I don't know which one I want to use. I'll probably just use sin. Convective inhibition. And that is true down here as well, right? So this is NBE or sin. And really the one down here is what we call a cap. NBE stands for negative Boyd energy. Sin or cinch, convective inhibition. Cap is just like a lid or a cap, like a baseball cap. So over here, Tim, you were right before. This is the tropopause, because the temperature is going down. Now, obviously, the actual environmental temperature is going to be different. It is what it is, and we would have to measure it with the radiosonde. But we know that at some point, the temperature doesn't get colder anymore, and now it starts to get warmer in the next layer. What's the next layer up? What's the layer above ours?
Stratosphere.
Right? So we got the stratosphere up here, and that's our typical sounding. Now, in this case, the question is, what is the environmental lapse rate? Would you at least agree in this scenario, the environmental lapse rate is less than the dry adiabatic lapse rate, but it's greater than the wet adiabatic lapse rate? So if I look at this line here, right, I'm looking at this line. It's less than the dry, and we know this is the dry, but it's less than the wet adiabatic, which early on is like that. So we know that that's the case. The wet adiabatic is less than the environmental lapse rate in here. And when that's the case, we're going to see there's a name for that, but we're going to be able to get to an LFC. Now in here, the question is, well, what goes on? What is happening here? I take a parcel and I have to lift it. If I lift it to the LCL, I'll get a cloud. But when I let go of it, once I start getting a cloud, do you understand that the air will not rise on its own? It will not rise on its own until the LFC. So if I have a cloud in stable air, we call that a stratus cloud. So stratus is stratiform, which means layered. It forms in stable air. Okay? If I lifted the parcel to here, I would get a cloud. Now, if I could lift it to the LFC, what will the air start to do once I get to the LFC?
What?
What happens when I get to the LFC?
Yeah, give off latent heat.
Well, it gives off latent heat whenever you've got a cloud. So even here it does, right? That's why it's wet adiabatic. But once I get to the LFC, what will the cloud do? Aaron, what did you have?
E. X. She says expand.
New. Sam?
Starts to rise by itself.
It starts to rise by itself. If that's the case, we say it's convecting. Air rises by itself, which is exactly what you need to say. And therefore, this becomes a cumulus cloud. Cumulus is puffy, and it indicates instability or unstable, right? and the cloud will go up. If it goes up high enough, and we're going to answer this question before the end of this unit, it will eventually create snow that will start to fall, and it melts into rain, and the rain falls. Once we get rain falling, we say it is a cumulonimbus, right? I think we've already talked about this, right? We've already used nimbus, meaning the suffix is rain. If it rained as a stratiform cloud, it would be a nimbostratus. I think we've already mentioned that. Okay, so when it rains, what do we call that rain? Technically, it's a shower because it's coming from a convective cloud. So convective clouds produce showers. Now, I'm going to do something for Sam. And really, the rest of you can watch it, but this is just something for somebody who's a meteorology major. So when I look at models, Sam, I can look in here at precipitation totals. How much precipitation do I think is going to form, right? I've got these areas of precipitation. And that's fine. I've got a whole bunch of stuff up there in Canada.
Great.
But I can also do convective precipitation, which is going to be a lot less. In other words, I can tell the model that only show me where there's showers expected. And that's convective precipitation. So if we look, where's there convective precipitation showers? We have an area of maybe showers and thunderstorms across Kansas in a couple days. We go forward, there's stuff over Florida, maybe up the West Coast, but I really don't see a lot of convective precipitation in any time until about then. This is coming in next Tuesday night. And we have an area where we might actually get convective precip. And if I get convective precip in this time of year, it showers. I can look at a model forecast and says, well, how much CAPE do I have? I have a little bit of CAPE. And if I have any CAPE and it's convective precip, then I have a chance for showers and thunderstorms. It's a little bit too far in the future to guarantee that, but
definitely something to watch.
I'm actually looking at our first potential for you, Sam, and for us, that maybe this weekend, or not this weekend, but the following weekend, we might get some showers and thunderstorms. We actually there's a little bit of a chance coming up a week from Wednesday, but until then, probably not going to get thunderstorms, but we are in the season. The spring has started where we have the potential for thunderstorms. We're looking at CAPE, which tells me the year is unstable. And then we look at precipitation products, which says convective precip says I have the chance. Obviously down here, I'm expecting thunderstorms, and that would be the first possibility of maybe severe weather.
I would expect severe weather down there.
Well, we'll see how bad.
Given the strength of that system.
Well, the dew point's too low. In fact, if you look at the dew point, when I look at the dew point, the blue is in 60-degree dew points, and I don't usually get that excited about severe weather until the dew points are on 60 in the plains. And so if you notice, the dew point really struggles to get up there, maybe into Texas and Arkansas. But around here, it gets in the 50s, and that's definitely, you're going to see a possibility of thunderstorms. And then there's another surge of 50s, maybe 60s. So it's the GFS, so I'm not too worried about it. But it starts to look in this area where I start thinking thunderstorms down here, Texas, Oklahoma, Arkansas, Louisiana, that kind of thing.
We'd call that a moisture tongue, right?
Yeah, Sam. Well, everybody can kind of follow what I'm saying there, right? Another product that we use for moisture would be what we call, I'm going to use PWATS, precipitable water. Whenever I see precipitable water coming back, that's usually when I see thunderstorms. So there's a possibility of some light showers, thunderstorms into Kansas. Dry.
I like how
there's the potential on Tuesday.
I like how it wraps around the system, like that in the Dakotas. That's
yeah.
really cool.
That's the moist conveyor belt, Sam.
Yeah.
Then another surge. So whenever I see this on what we call precipitable water, like that's pretty impressive for the weekend of that Saturday, March 13th. I would say based on the models right now, I'm looking at a potential for thunderstorms that day. Whether or not they're going to be severe, we'll see. I certainly have wind shear, which is what I want, but it's fun to see this situation is not all dry. It does get dry after that, but we notice. I'll show you something. Want to be happy? I think most of you will be happy. If I look at precipitation type, look at what I don't see. I don't see any snowfall for a very long time in our area. Up in Minnesota, yeah, there's our first chance of some light snow on the wraparound. After that goes through, a cold front comes through, turns over to snow.
That's a strong system.
That's going to probably produce severe. So that's the one I'm looking forward as the first spring event. This is your first spring event right there, a week from Saturday. Yay. Okay. If this is true, this is a model. You take models for
Well,
what?
you're the expert, so
I've been looking enough times to know that, yeah, that weekend looks like there'll be something. I wouldn't want to go out on a limb and say anything. So I just thought I'd show you how it plays out in reality. But we get cumulonimbus clouds. The air starts to accelerate up. Okay, so the air accelerates up in this area. Okay, now, how high does the cloud go? Do you understand that in order to get the cumulus cloud, I need to lift it to the LFC? So in order to get a shower or a thunderstorm, I need to lift it to at least the level of free convection. I can get a cloud if I lift it to the LCL, but I've got to lift it higher than that if I'm going to shower and thunderstorm. The question is, this air, this instability, CAPE, causes air to accelerate. So I want you to say instability or CAPE causes air to accelerate upward. Do you think we could cause air to accelerate downward? Yes or no? Do you think air can accelerate downward?
feels this is a trick question. Think you can?
If we have it, we call that D-CAPE, downdraft CAPE. So yes, it can go down. But we are going to really only be talking about air accelerating upward. So what does convective inhibition cause? What does convective inhibition cause? I don't know where everybody is today. We need you guys talking more. You can't just sit there and not talk. So Isaac, what do you say, buddy?
I'm not sure that I have an answer.
Aaron says stable.
It is stable air, Aaron. So do you understand that unstable air causes the air to accelerate upwards? So what does stable air do?
Slows down.
Right? If unstable air causes it to accelerate, in other words, speed up, going up, then stable air is going to cause it to slow down. So the question is, how high does the cloud go? Where does this cloud reach its top? In other words, where does the cloud end? Where's the top of the thunderstorm? What do you think?
She says the EL.
Do you guys agree with her or disagree? Thumbs up. Thumbs down, something like that. No. And survey says not even close. Do you agree that the EL is the starting of stable air? So it starts to slow down. It doesn't stop it. When does your car stop? When you put on the brakes? What determines where your car stops? What determines where your car is going to stop?
How hard you like push on the brakes?
Okay, how hard you brake. What else?
When you brake?
Well, I mean, we're assuming you brake. How hard you brake will determine where your car stops. But what two things really matter besides how hard you brake?
How fast you're going?
How fast you're going, and what else? More than just how fast.
The terrain you're on?
No, let's just assume the same terrain. You think it's as easy to stop a train as it?
Mass of the car?
Ryan?
The mass of the car?
How about the mass of the car? So if it's the speed and the mass, what is it really?
Mm,
What's the word I'm looking for?
Momentum?
It's the momentum. What's the formula for momentum, Ryan? Long as you're 2 for 2, let's go for 3 for 3.
I don't remember.
Oh, 2 for 3. Well, that's, like baseball. What's
MV.
what's the formula for momentum, Tim?
MV.
MV. So it has upward momentum, mass times velocity. And what we're saying is that the greater the mass or the greater the velocity going up, the further your car is going to go when it starts braking, right? I mean, hold on. I'm having a problem. There we go. Okay, so the faster the air is rising, the farther it will go before it brakes. So what's the strength of the brake? The strength of the brake is the NBE. But how fast will your car go? What determines how fast your updraft will go within a thunderstorm?
How high the cape is?
How much cape there is, right? So where will the clouds stop? It won't stop at the EL because what happens at the EL is that's where the car starts to brake. That's where it starts to slow down. But the cloud will go up until the PBE between the LFC and the EL is equal to the NBE above the EL. Or maybe the other way around. The cloud will stop growing up when the NBE above the EL is equal to the PBE between the LFC and the EL.
mm,
Write that down.
Can you say it again?
Who said say that again?
Me, right.
Why do you need me to say it again? Look at the stuff. Look at the stuff, Ryan. And I want you to think it through. What's causing the air to go faster and faster?
The PB,
Right. What's causing it to slow down?
the NB,
So when the NBE, which is what color,
orange,
is equal to the,
PB,
which is purple, right?
Right.
So now instead of saying orange and purple, where is the orange? Julia, where's the orange? Oops, your mic's not working. Oh, your mic's not working. You know what you guys need to do? You need to write a letter to the College of DuPage people, administration, board, and start complaining. They want to go online in the fall. And you should say, you know what? You're going to screw me over again. You give me my money back. I think you should protest what they're doing. Lena,
I totally thought we'd be back by fall.
well, we should be. We should be back now.
Yeah.
You know, the reality is, if you gave me the choice, I would be in the classroom without a mask. I'm so angry right now. You could be at home. If you want to be at home, be at home. Anybody who's afraid, be afraid. But I want to be back. I'm done. And you should realize they're screwing you over. I mean, we're sitting here, I'm trying to have a conversation with Julia, and now her mic's not working. And it's like, really? How annoying is that? Julia, did you get your mic working?
I don't know. Can you hear me?
Yeah, I can hear you now. There you go.
Well, the orange is like either below the LFC or above the EL.
Which orange is slowing down the air?
Oh, the one above the EL.
So when the NBE above the EL
Mhm.
is equal to, right, same area as,
The PBE,
and where does PBE exist?
in between the EL and the LFC.
But I want you to always think going up. So between the LFC and the EL. So where does the cloud stop? When the NBE above the EL is equal to the PBE between the LFC and the EL. Does that make sense? Now do you got that right? So what's the first NBE doing? What's this first NBE doing down here?
I mean, it's keeping a cloud from rising freely.
It's keeping, yeah, okay, I can accept that. It's keeping the cloud from rising freely, right? And the word that I would use is it's resisting. It's like, imagine that I was playing with the dog this morning, and I picked up the dog. I was playing fetch with it, and I picked up the ball, and the dog held on. Could I lift the ball? Yes, but that dog was resisting me, right? And eventually the dog fell, and then the ball goes crazy. So that first NBE is resisting motion upward. So I'm forcing the air up, but if I let go of it, it would come back down. So that first NBE is capping, it's resisting. It's like I have a Coke bottle here. What would happen if I shook up the Coke bottle and kept the lid on? Right? Would it explode? No. But what would happen if I pulled the lid off after shaking it? Then it would spray, right? So the cap that we say, another word that people sometimes use is lid. It's a cap. It's resisting that motion. Once I push the air far enough to get to the LFC, the air goes up. Does that make sense?
It's also use inversion, right?
Well, an inversion is just a stable layer, but the stable layer is in the NBE, dude. It doesn't have to be an inversion to be a stable layer. So in this case, the reality is my thunderstorm probably is not even going to happen, because the reality is I can push air to the LCL, but if the LFC is way higher, I'm probably not going to be able to push air that high. So if I could, this is what it would look like, but it's probably not going to be that. Now, one other thing I do want to kind of point out is what happens to a box of air that gets all the way to the top of the cloud up here? What does that box look at? What does it compare to the environment?
It's much colder.
Cooler.
So what's it going to do? It's going to sink, right? It's going to come back down. But if the box comes this way, now what's it going to try to do? Go back up. So the air actually starts to oscillate around the EL. It's very cold up there, and you create the anvil. So the anvil of a thunderstorm forms at the equilibrium level. That's something you should probably know. The anvil is made out of ice. A cloud that's made out of ice is called cirrus. So the anvil forms at the equilibrium level because the air, and really what the air is doing is it goes up and down and it oscillates like the spring. Sometimes you get the mammatus there, Sam, and if you remember that, but we're not going to talk about that.
When you know how there's like overshooting tops?
So
Does that air end up coming down too?
So that would be the overshooting top. So when we say we have a thunderstorm and it looks like this, there's the anvil of a thunderstorm, and that's the overshooting top. Make sense? And it overshoots because it's got upward momentum before that stability brings it back down. The faster it goes up, the higher the overshooting top. Okay, now the reality is this is probably not real, not likely, this scenario to get a thunderstorm. So let's look at a more realistic thunderstorm. So I'm going to do the same thing that I did before. I'm going to go dry adiabatically. After dry adiabatic, I go up wet adiabatically. But over here, my environment is probably going to look more like this. Okay? In here, notice that I don't have stability from the ground up. For this layer here, the environmental lapse rate is equal to the dry adiabatic lapse rate for a while. And that happens near the ground in the afternoon. So do you notice here, you have a lot less, and you still have a lot of CAPE, right? You still have a lot of CAPE there, but notice what's less is you have a lot less instability. I mean stability, CAPE, cap, SIN. Does that make sense? Let's take a look at something else. Let's look at one that looks like this. Dry adiabatic. Dry adiabatic. Wet adiabatic, something like that. Here's the environment. Okay. Now, guys, taking a look at this picture, label it. Shade in and label. Well, I don't know how you're doing it. This is what I would do in class. I suppose you could just snip this one, bring it into paint or something. So what is this?
Is that the LCL?
It's always the LCL because the parcel, even though it's hard to see it because it was there. Right? It goes dry adiabatic and then it goes wet adiabatic. So that's always the LCL. So what is this?
That be one of the ELs?
Why are you saying that's the EL?
Because it's the point where the environment becomes warmer than the parcel.
Right? Okay, so in other words, besides the LCL, what else is this line?
The LFC too.
Isn't it also the LFC? So in other words, this area is what you should think about. Oops. This is the area you should think about first. That's purple. This is purple. Remember, because the parcel in blue is warmer than the environment. And then what's this? That's orange. That's orange. Oops, I blew it. Didn't I?
It's the one above it.
That's purple. Ah! Yeah, hold on. That's purple. And that's orange. I guess I was using a darker orange here. By the way, when I erase something, it seems like when I erase it or undo it, it fills that color in differently. Does that make sense to you guys? Does everybody see why this is Cape? So what that, go ahead.
Oh, I was going to ask, is tropopause still up towards the top?
Yeah, so the tropopause would be, tropopause is still here. This would be the EL. What's this? What's that?
The LFC again?
Isn't that another LFC? There's no reason that you can't have more than one LFC, and that's the EL. Okay, so the question then becomes, what occurs? Well, where will the clouds start?
At the LCL.
At the LCL, what kind of a cloud will it be, Zach?
Would it be a cumulonimbus?
Well, it'll be cumulus, wouldn't it? Because when this time when the cloud starts, it's unstable. So as soon as it reaches saturation, it starts to rise by itself and accelerate. Now, when it goes to the EL, what happens? It starts to slow down. At some point, the cloud will stop. The cloud stops when the NBE above the EL is equal to the PBE between the LFC and the EL. Right? So in this case, in order to get a thunderstorm, where do I need to get the air to? I need to get the air to the second LFC. But this layer here is acting as a cap. It's stopping it. Would you agree that the orange area, just by eyeing it, looks more than the purple area? Say yes or no. You see what I'm saying? Okay, so in that case, the cloud goes up, but it doesn't make it high enough to get to the second LFC. In that case, we call this a TCU. TCU stands for towering cumulus. It doesn't get high enough to start producing precipitation. That needs to get up here, higher up in the troposphere. So the question is, this cap is stopping convection. Stability suppresses convection. Now, Sam, because you brought this up before, do you agree that in this case there's an inversion? Right? So there is an inversion. In the race to get cold, in this layer, what's the atmosphere doing? It's getting warmer. It's losing the race. Question is, when would I get a thunderstorm? Well, I get a thunderstorm when the cap breaks. When does the cap break? When the PBE between the LFC and the EL is greater than the NBE between the EL and the next LFC. Write that down. When will the cap break is the question I'm asking. When will the cap break? And what's your answer? Can you write it down? I do this on purpose. My hair is crazy today. It's all staticky, and every time I turn my head to the side, I'm like, whoa, it's weird. So Ryan, were you able to write it down that time?
Is it the cap will break when the PBE between the LFC and the EL is greater than the NBE
Between,
between the LFC and the EL?
no, well, remember, think down up. So everything you did until the very end. So when the PBE between the LFC and the EL is greater than the NBE between the EL and
The LFC?
the next LFC, right? Because there's two.
Okay.
So we're going to the next LFC.
Yeah.
That makes sense?
Mm-hmm.
Now, in this case, does it look like that cap is going to break?
Mm,
Does this orange area look less than this purple area?
mm,
So the question is, how do I get rid of the cap? First, there is the dew point must be here someplace. So the dew point and the temperature, remember they get closer to, the dew point's going to go down by 2 degrees Celsius per kilometer. You know what, let me do this. That's the dew point. That is the temperature. What do you call the difference between the temperature and the dew point? What's that called?
Dew point depression.
Okay, so do you agree that the temperature will go down by 10 degrees Celsius per kilometer? That's the dry adiabatic lapse rate. What's the dew point going to decrease by?
2.
So what if I increased the dew point? What if I increase the dew point to, let's say, here? What I'm going to ask you now is looking at this graph. So if you need to, what I would suggest, do a screen grab. If you have a Windows Shift S, and you can copy this and open up Paint or whatever you want to use and put it in there so that you have it. I'm going to break you up into groups. And I'll tell you what I want. So can you guys do that? Screen cap? Are we good?
I can't get it.
You have a Windows machine, Kevin?
Yeah.
Yeah, so Windows Shift S. See, it should open this up. And then you can just use your mouse to grab it like that. And you know what I guess I could do? Did you get it, Kevin?
Working on it.
Here, hold on. Let me do this for you.
I had it and I lost it.
Let me do this. Where are you, Chad? Oh, I lost it too. Well, somebody else in your room probably has it. So I'm going to break you up into 2 rooms. And what I want you to do is tell me when I increase the dew point, write down as many things as you can that happen as a result of a greater dew point. Does that make sense to you? Say yes or no.
Yes.
All right. You guys are in good shape right here. Okay, ready? Go. Okay, we're back, or at least should be back any second. So here is your stuff. So what we're going to do is we're going to increase the dew point. And so when we increase the dew point, we are now going to get a, this is the way it will be. So I'm going to use a different color blue.
You're not screen sharing.
I will now use a different color blue and actually share the screen. Thank you for doing that. Okay, so what I've done is I create a different LCL, right? The LCL is going to be lower. And when I do the wet adiabat over here, do you understand now that look at this amount of cape will be much bigger. This amount of cape will be a lot bigger, right? And then there's basically no other, there might be a little bit of NBE in here. This NBE gets eradicated somewhat. So the EL goes up higher. This goes away. I mean, it's more way up here. The new LFC is lower. There might be an EL, but it's a lot less, right? There's before we said the NBE was bigger than the PBE. Now it's not, right? So we get rid of all this NBE. I wish I could just erase that. A little bit hard to do that, I suppose, right? I lose all this stuff. So what you think about it, let's think of all the things that we would do. And I'm just going to say this, I don't want to take the time to write it out. The LCL is lower. The first LFC is lower. The second LFC is lower. The ELs are both higher. I have more PBEs in both places. I've got less NBEs. The storm will probably not be capped, right? This purple area is now bigger than the orange area, so the cap will not hold. The thunderstorm will go all the way up. Its top will be higher than it would have been. All of these things, all because all I did was increase the dew point by a little bit. But increasing the dew point also says that the dew point depression is smaller, which means that the relative humidity is what? Higher, right? So the dew point's depression smaller, the relative humidity is higher. All these things, all because I increased the dew point by a little bit. So Sam, think about next week what I said. I said, there's a possibility, there's a little bit of cape, but it's only bringing up the dew points into the 50s. Well, what if the dew point hits 60? That little bit of extra dew point can make a difference between 400 K, and 1200 K.
Right.
Much more likely. So that's why it's the instability of the atmosphere is super sensitive to the dew point, more so than the temperature when I'm in a thunderstorm environment. So you need to go back into the lecture and grab all those things if you didn't get them down. But does that make sense to you all? Now, I have not graded your essays yet. I've seen them. Did you do a good job on your essay parts?
You think so?
Give me a 1 to 5. How well you think you did on those, on the essay parts of that last test?
4.
4. Okay. I mean, it's hard to tell. I don't know what it's going to be. Looking at things, what do you think you could do to be better? Lena, what do you think? I mean, you're getting so I've had Lena since August, right?
Mm-hmm.
I have no idea what you look like. I know what your face looks like. And actually, what was your name last semester?
It was Abby, because my
It was
sister.
Abby. What got you better on things?
Yeah, I would say like going over stuff more, because I definitely at the beginning thought, oh, because it's open note, I could just go right into the test. So definitely like reviewing like it was an actual test in person.
Yeah, that's a great thing. How are you doing in your notes?
My notes are good. I'm trying to think.
Right, her notes are getting even better. Right, I keep saying you're doing a great job. So
Thank you.
here's the thing that's challenging, I think, for you all people. You need to practice communicating the answers down. You're all fine in class. Like your participation, you're listening. You guys are great. I'm happy. You make me happy. You know, happy teachers try to give good grades. Just so you know, that's how I think. When I'm grading your paper, I'm like, oh, I like you, so I'm going to give you more points. It's kind of the way it works. But when you're doing the essays, you need to be able to express the ideas better. My biggest problem with people in their notes is that they're just scribbling stuff I've done rather than expressing that they know it, right? Because I have no other way to do this other than you showing me that you know it. So do you think that what I just went through with you sounds like it could be an essay question on the test? So if you start doing it now and writing it up really well, you will have a much better chance when I ask you to do it on a test. So take the time and talk about why the dew point changes matter so much. And really go through it. And so Sam, you were looking at the diagram, right? You start seeing it when you redraw the diagram on your own, you start to see the difference. And then that's just something that you all could do to be better at it. Make sense? All right. Let's do this. Let's go to you turned in your water vapor lab. Whoops, wrong class. You turned in your water vapor lab, right? And then the other lab is going to be due, I don't know, today, tomorrow? No, before class on Thursday. The instability lab. And there's a lot of things in here that we talked about. See, look at this question here. How long do you think that should take you? What kind of an answer do you think I'm expecting for this one? If you want an A. If you want a D, you don't have to do much. Do you agree that it has to be talked out pretty well? Because we spent a lot of time with this. You have diagrams that you can show me. You've got words that you can use to express this. So I think this is important. Now over here, this stuff should be fairly simple, right? And now we have the ability to answer question 4 and then look at question 5. And you have another chance to practice. And then we have this. Now, did you do this? How many, talk to me about what you were able to do.
I got through 5 and that was it.
So do you know what you're doing here? The only thing here now is that rather than just drawing the red line, you're actually going to draw the red line based on the data I give you. So keep in mind that the environment temperature is this. You'll plot that up on a good graph paper. Now, do you have good graph paper? Can you get graph paper online? Then use it. If you're going to do an online drawing, you got graph paper online. Draw on it or insert it into Paint or whatever you're doing. If you're doing it at home, you should have graph paper or print out the graph that you can print out. So there's no excuse not to be able to do that. And I'm saying that you're going to do it 2 ways. The first one is the LCL at 2 kilometers. The second one, the second time you do it is the LCL is at a ½ kilometer. Now, what would cause the LCL to be so much lower? Obviously, a higher dew point. Keep in mind that on here, keep in mind that the air always cools dry adiabatically until the LCL. And then what's it do after the LCL? Wet adiabatically. And what are we using for the wet adiabatic lapse rate, even though I hate it? 6 degrees Celsius per kilometer. So you're going to do that, and you're going to graph up the red and the blue, and then you're going to label the LCL and LFC and all this stuff. Does that make sense? And I'm asking you for the environmental lapse rate between 2 and 4 kilometers. Well, and we've done this before, right? The lapse rate is the change in temperature over the change in height. And from 2 to 4, well, let's do it from 3 to 5. What's the difference in temperature?
Well,
12. And what's the difference in height?
2.
So it's going to be 6 degrees Celsius per kilometer. And that's the unit of lapse rate. So this is all easy. The only thing you can't really do is knowing the stability of the atmosphere. So that's what we have to get to next. But everything else on this lab should be pretty straightforward. Do we have a problem? Anybody do this stuff? I kind of doubt you did this section. And the same thing is true of this. Now I asked you this question, and I'm asking you this question. Okay, but in this question, what did you say? Like, what have you independently figured out about stability of the atmosphere?
So I just simply put the environmental lapse rate has to be greater than the lapse rate of the parcel, and the parcel must be saturated.
It's part of it. What the rest of you? I mean, again, you're independent on this. This is stuff that you're doing in the book, right? You're doing your chapters in the book or those worksheets. So what did we talk about in there? What did you have? Isaac, what did you got? What did you have for that?
For question number 2,
Yeah.
I wrote the unsaturated parcel is cooler than the environment and will sink back to the ground. The saturated parcel will be warmer than the environment, become buoyant, and continue to rise.
Okay, Isaac and Tim, I want you to have a conversation with each other using words and express your ideas as a conversation so that we can all listen in on what you're saying. So, Isaac, why don't you start with kind of expressing what you said again? Because, you're talking out loud, right? You're just using words and it's hard to listen. So, but this time, I want Tim to really listen. The rest of you listen in and see if you can express it, okay? So be a teacher, don't just read your answer.
I'm not really sure what you mean by express.
Well, I mean, you read the answer. I think what you had was good. Julia, did you understand it?
Yeah, it made sense.
Okay, so express it though again. So teach us. You be the teacher. Isaac, where do you work?
Work?
Yeah.
I don't really have a job right now.
Well, where did you work in your life?
The most work I've done is watching my cousins for my aunt, but that's really it.
Oh, you haven't had like a go out and get a job?
No.
Are you involved in any sports or activities?
I'm not a sports person.
Other activities? Music, drama?
I do a lot of art. That's really it.
Okay, what kind of art do you do?
I like to do watercolor.
Okay, so tell me something about your watercolors, Isaac. I want you to. Have you ever done a painting?
Yeah, I've done paintings before.
How do you set that up?
Well, if it's on a canvas, then you have the canvas and you don't have to, but you can put primer on it so that the acrylic doesn't go through the canvas, and more so.
Acrylic, what's that?
Sorry, what?
What do you mean acrylic?
Acrylic, it's a type of paint. It's different from watercolor. It's more thick.
Oh. So how many colors are you using?
It depends on really what you're going for. You can use a few colors to multiple different colors.
You layer them?
Yeah.
What happens when you do?
Well, sometimes if you wait for the acrylic to dry, then you can paint on top of it and it won't blend together. And if you want to blend the colors together, then you have to be really quick so that the paint doesn't dry.
Okay. Now, I want you guys to think about something that we're doing here. Who's running the education right there for the most part? Who ran the learning right there?
Isaac.
Really? I thought I was asking all the questions. Did you learn about how you can overlap them if you let it dry, or you can blend them if you keep them wet? Did you know that? I didn't know that. He didn't volunteer that. You explained it. How sophisticated was it in your explanation? Did you use a lot of fancy words, Isaac?
I'm not really sure.
I mean, you just kind of said stuff, right? And I asked you questions and you talked about it. So I'm asking you to define what conditional instability is. You wrote something. Just talk to me about it. You don't have to be formal sounding. You don't have to sound like you're not lecturing to PhD students. You're just talking to people, explaining what's going on. And then Tim or Julia get involved in this too. As he explains, ask some questions. Or you ask questions. I don't care. It's a conversation.
Well, when the unsaturated parcel is cooler than the environment, it sinks back to the ground because that means it's stable.
What's stable? Okay. So now what I would say to you is what's stable? What? You said it's stable. What's stable?
Is it the environment that's stable?
Ryan, what do you say to that?
I think the air parcel would be stable.
When is that going to happen?
That's going to be when the environment is cooling faster than the air parcel.
Okay, you've talked about something different than what Isaac said. Tim, what was different about what they just said?
Ryan was more talking about cooling, and Isaac was talking about like stability and all that
Of the what?
of the parcel.
Okay, so in other words, when I use the word stable or unstable, and maybe even neutral, which you guys, we did that with, remember you gave me the little marble on the pole and stuff like that? When we use those words, we are referring to the parcel. We are referring to the parcel when I use those words. So what is stable? The parcel is stable. The parcel is stable if what? When will the parcel be stable? I need an answer.
The parcel is stable when it's cooling faster than the environment.
Don't predict. Tell me when it is.
Didn't I just do that?
No. You said when it's cooling faster, present and perfect tense. You're saying that there's an activity. I'm saying it is stable right now. It is.
When it's colder than the environment.
Huh?
When it's colder than the environment.
Okay, if it's colder than the environment, therefore it's what? Anybody? If it's colder, it's what?
Unsaturated.
No. Sam.
Yeah,
If it's colder, it's what?
less, it's,
What'd you say,
I was gonna say less dense, but
Aaron?
Denser.
Right. I don't even know if this is right. You know, I once heard a podcast talking about when do people go more dense or denser. You know what the rule is for that? There are no rules. There are no rules. It's just whatever people say it is. So most people would say more dense rather than denser. I don't know. But do you agree if it's colder, it's more dense than the air around it?
Mm-hmm.
That means it's stable. It is stable. But when I take a parcel on all those soundings, what is a parcel really just? How's that for a question, huh? How's that for sounding intelligent like I'm talking to PhD people? What is a parcel really just? It's
Air.
really just what? What is a parcel really?
Some air in the atmosphere.
It's just some air. And I start a parcel from wherever it is. So do you agree that the parcel always starts with the air that's around it? That's where I collect it. So when I start the air, the parcel and the air around it are the same. What do I do to the parcel then?
Lift it.
And then I compare it to the air around it. So if it starts the same as the environment, what does it do after I lift it? I don't know. It depends. It depends on what? What the environment is doing. Now, Tim, if I want the parcel to be colder, to be stable after I lift it, what must be true?
So now we're predicting, right?
Yes, or at least present and perfecting.
So it has to be cooling at a higher rate than the environment.
It has to be cooling at a greater rate than the environment. So how is it cooling? Well, it's cooling dry adiabatically. And it must be cooling at a greater rate than the environment. Right? And Isaac, you said if the parcel is what?
Unsaturated.
Right. And so rather than say unsaturated, we would say dry, which really technically is unsaturated. So you could say unsaturated and that'd be fine. But you could have just said dry. But what if the parcel was wet? Then what must be true? Are you guys following me? It's so damn hard in this, right? What I really want to be doing is sitting. I want to be sitting on the floor talking to you about this because right now you're on a screen and I'm just ready to scream.
So if the parcel is wet, that means it's warmer.
Why?
Well, because latent heat is released when water vapor is condensed.
And what would make the parcel warmer than the air around it after I lifted it?
It has to be saturated.
And if it is, what's it doing?
It's condensing water vapor, releasing latent heat.
But remember, I want the parcel to be unstable when it's saturated. So what must the parcel be doing?
It has to be cooling at a lower rate than the environment.
It must be cooling at a lower rate than the environment. But how is the parcel cooling?
What adiabatically?
So it must be this. But if I put these three thoughts together, I get this. And that is the criterion for conditional instability. The environment has to cool somewhere between the environment or the parcel's dry adiabatic lapse rate and the parcel's wet adiabatic lapse rate. So if the parcel cools wet adiabatically, the air will be unstable. If it cools dry adiabatically, it'll be stable, which is what you said, Isaac.
Sorry,
you just have to figure out that you said this. This is what learning is. Learning is not memorizing a bunch of facts. It's piecing together information to make a cohesive thought. And then communicating that thought to another human being. You do that, you've learned something. The question is, most students don't. How are you? Are you getting to that point where your thoughts can be explained? That's what an A student is. A student who explains something and gets it. They're going to get an A. I feel bad because a lot of you get A's if you work hard, as that's supposed to mean something. How many of you have taken a car to a mechanic? Do you pay the mechanic based on how hard the mechanic works?
No.
Pay the mechanic on whether or not that mechanic can fix your car. So what students should get an A? Those who work hard or those who get the material? I don't know. It seems reasonable to me to expect that you have to get the material. If you get it in your head, what level are you at? And you have to prove to me that you do it, which means you have to communicate that to me. How do you communicate that to me? By talking out loud and writing it down in essay form.
Well,
That's what I look for.
for some people, you have to work hard to get it.
Well, everybody has to work hard to get that point because you only think it's hard because you haven't really ever been forced to do that. You memorize some stuff, you get a list, you use flashcards and you think you're learning something. That's not what I want. But it's way more fun because when you get something, isn't it better when you're like, oh, I get this? And then you know what's the best way to show me you understand something? This is kind of an upside down theory. Do you know when the student does this, I know they really understand it. What do you think I'm looking for in a student? What do you think? What do you think really solidifies my looking at a student and going, yes? What do you think they need to do? Zach, what do you think, bud? And not many of you in this class have done this yet. You have to ask me a good question. If you ask a really good question, that usually tells me, oh, you know what you're talking about, because you can see the other things beyond the information I give you. You're like, oh, wait, there's something else. And you start to piece together the future. You're actually predicting knowledge. That's what's really cool. I tell you what, let's try this. I'm going to show you an abstract way to discuss what we just discussed. These are isobars. And what I'm going to do is I'm going to pretend it's something like this. So watch this. And I'm going to say that the pressure here is some value P. Which way is up? Oh, that's stupid. Which way is that way? Which way is this arrow pointing? Up, because this is cross section. If this was a map, which way would that be pointing?
North.
This is a cross section. So what's the value of pressure on this line?
DP.
No. Is it this pressure, P?
Okay. The chain. No, it's the same thing. Never mind.
No, you're see, Tim, you're thinking, I see it. Is this the same value? No. If it's not the same, it's
Different.
how different is it? What do you think, Ryan? How different is this pressure?
would be like pretty significantly different.
Well,
I don't know like the exact value.
Isn't P just arbitrary? It's something. Is this, let's say it's 1,000 millibars. Is this 1,000 millibars? No, it's less than 1,000. Well, how much less? Well, it depends on what the difference is. So let's say the difference was 100 millibars. This would be, what's the value of this line then? 900. It'd be 1,000 minus 100 because it's 100 millibars different. Does that make sense? So does that make sense? Yes or no?
Oh.
Because if you don't get it, that's okay. I'll rephrase it. I'm okay with that. So I start a box there. And when I start a box, what's the most important thing that I know of the box? It's temperature. It's some temperature. By the way, Tim, if you see this, bye. Tim had to go. He let me know. Now I lift the box from P to P minus delta P. What does the temperature of the box do?
Decreases.
By how much?
$10 degrees per kilometer.
You're assuming what?
That's what.
What are you assuming about this parcel? If that's the case.
Assuming it's dry.
Assuming it's dry. How far is it? How long is it dry? See, Aaron, this is kind of good, right? You're being the writer and the English person and stuff. So you understand how important words are to communicate, right? So how long is this parcel dry? What do you say? Lena, what's the answer to my question?
Is it until it's, see, I don't.
Well, as in the picture, as in the drawing, Lena.
Is it dry until it hits the pressure that we don't know, so the P minus the change in P?
Well, in this picture, how far is that? Simple word. How far do I lift it dry adiabatically? Isaac? Sam? Just everybody keep your mics on. Talk to me. This is conversation. This is your brain working. How far is it dry?
Would it just be delta P?
That sounds really technical. I want it to be simple.
Aaron says the LCL.
There's no LCL on here.
Okay.
Not yet. So according to the picture, how far did I lift it dry adiabatically?
Good until you stop the line.
Well, wouldn't that be the whole way? How hard is that to say that? How far did I lift that parcel dry adiabatically? The whole way. And now what's the temperature at this place? Well, I'm going to call the temperature here. Hold on. And I'll tell you what, I'll come back to that in a second. What am I doing here? What's that line represent? What did I do with that line? Sam?
You increased the temperature.
I did what? Explain that.
Well,
How is it that you see anything in there that says, I increased the temperature?
moved it up.
Where did I start the temperature?
Started the temperature at the same place, but the temperature doesn't decrease as much.
Okay, well, that's a totally different thought. I didn't
That's-
increase the temperature.
I meant to say
Just
that.
said I started at the same temperature. What temperature did I start it at?
T,
Right. What color T?
red.
Right. Did I start it any differently? What's
No.
the difference what did I do with the box this time?
Just lifted it at a warmer. You lift. How do I say this?
That's a good question. That's a great question to ask. I'm willing to wait for you.
You made the parcel warmer.
Well, the parcel is warmer. Why? I lifted it how? Anybody else? Go ahead. Jump in here.
At a warmer lapse rate.
I wouldn't say a warmer lapse rate. That's the bad choice of words. What's a better way to say it?
Positive lapse rate.
They are all positive. That's not the best.
It's just a lower lapse rate.
At a lower lapse rate or slower, you could say lower or slower. It's a less lapse rate. The lapse rate's less. Remember, dry, less than that. What rate is it? You look at this line, what do you see? What lapse rate is this?
The what adiabatic?
Isn't that what you would say? It's the wet adiabatic lapse rate? All right. So do you agree that if I lifted it at the wet adiabatic lapse rate, then I could say what word? I lifted it how? Use a word. Adverb. How do adverbs end? What letters end in an adverb? I feel like I'm going to teach you more English.
Is it ly?
And so how did I lift the parcel with this
What
second?
adiabatically?
Didn't I lift it wet adiabatically? Hey, Lena, how far did I lift it wet adiabatically?
Ooh, as far as the line goes,
What's the
Absolutely.
answer?
As far as you lifted it,
Well, in this case, how far did I lift it dry adiabatically? What was the answer to my first question? Ryan, jump in here. Come on, guys.
Oh, all of us. Just the whole way.
The whole way. How far did I lift it dry adiabatically the first time? The whole way. How far did I lift it this time? Wet adiabatically. The whole way. Do you agree? Over here, I'm going to call the parcel TH. What do you think H and C stand for?
Hot and cold.
Okay, hot and cold. So what I'm going to say, now watch really carefully, watch this. I have a parcel of air at some pressure P. I'm going to lift that parcel to some lower pressure, P minus delta P. The coldest that parcel can become is TC if I lifted it dry adiabatically the whole way. The hottest that parcel will be, or the warmest, is if I lifted it from P to P minus delta P, wet adiabatically, the whole way. Can a parcel starting here at P, lifted to P minus delta P, can it be colder than TC?
Oh,
Nope. Can it be warmer than TH? Can it be in between?
Yes,
Why?
because it could cool dry adiabatically and wet adiabatically.
I could go dry adiabatically for a while, and then I would cool it wet adiabatically, right? If I reach the what?
LCL.
Somewhere what's the word?
somewhere along the way.
Okay, I can accept that. I was going to say somewhere in between, but I'm perfectly okay if you said somewhere along the way, you found the LCL and now it started changing the rate of cool. So this represents, right? This represents the limits of what that parcel can be. That the parcel will fall somewhere between TC and TH. And I'm using cold and hot because I don't want to use warm, because if I said TW, what might that trigger in your brain? At least hopefully it would. What does TW stand for?
The temperature of the mixing ratio, or
No. Although I know why you said that. What's TW? What's the word, Aaron? Are you spelling something out?
Yeah, the warm T. No, what?
Are you struggling through getting the right?
She's still spelling it. P. Warm vapor. Warm vapor. What?
No, TW. What's it stand for? Right, we did this last week, right? TW is the wet bulb temperature, which measures the effect of, everybody?
Evaporative cooling.
Thank you. Wet bulb temperature measures the effect of evaporative cooling. What is the instrument that measures the wet bulb? What's the instrument called?
I know what it looks like. It's the thing that you swing around, right?
Right, but when you don't swing it, you remember the word?
Flingometer.
Slings, yeah, okay, close. So sling psychrometer. That's just right. That's not really learning, other than it's just, oh, that's sling psychrometer. Yeah, yeah. So that measures the effect of evaporative cooling. Right, that's what the wet bulb temperature is. And by the way, what has a temperature of the wet bulb temperature? What is a wet bulb temperature? We did this last week. Didn't we say it's the temperature of a raindrop? Hello, McFly. Temperature of a raindrop is a wet bulb temperature, right, guys? This is on the sheet. What's the temperature of a raindrop? And you should say TW. I said, what's the wet bulb that measures the effect of evaporative cooling? And the instrument that measures it is the sling psychrometer, right? You got that? You have it on this sheet? You turned it in? Are you looking at it? Everybody okay with that? I mean, that's not really using your brain too much, other than that's what it is. You have that though, that information? Are we okay with that? Say yes or no.
Okay, yeah.
Yes.
You know what I want you to do? I want you to talk to a friend in person or your parent or something. I want you to talk to them and have them not answer you and tell me how that feels. You're looking right at them and you ask them a question and they just look at you and don't respond. Tell me how that feels. And then when you feel that, I want you to understand that's how I feel every time I ask a question and you guys are silent. That's my emotion. Does that feel good? Okay, so thank you for at least nodding. Do you understand wet bulb temperature?
Yes.
Okay, good, beautiful. Now, I do not, that's why I call it TH, because I don't want you to think that. So this is the temperature the parcel can be. Now, the question is, what is the environment's temperature?
Whatever it wants to be.
And the answer is whatever it wants to be. So what I'm going to show you is, well, what if the environment's temperature, remember, the environment's temperature starts at the same as the parcel. But what if that's the case? So what I'm going to do is I'm going to say this is case one. The yellow. And how would I write what the environment is doing?
Do you want it in words or do you want it with like the gamma E?
Well, you could just use words and then you could tell me the equation to write down.
Okay, so like wouldn't the environment be cooling faster than the parcel?
Okay, the environment is cooling faster than the parcel. So the environmental lapse rate, gamma sub E, is what?
Greater than the
Greater
dry
than-
adiabatic?
Okay, do you agree it's greater than the dry adiabatic lapse rate? Do you also agree that the dry adiabatic lapse rate is always equal that, or is greater than the wet adiabatic lapse rate? So do I need to write this? Not really, because I know that this relationship is always true. But in this case, the environment is cooling faster than the dry adiabatic lapse rate. So what can we tell about parcels lifted in an environment that cools faster than the dry adiabatic lapse rate?
Unstable.
What?
Is it unstable?
The parcel will be unstable. Why?
Because it's cooler than the environment, so it would be rising.
Because, well, hold on. Because the parcel's cooler than the environment, therefore the parcel is,
Less dense.
Less dense.
okay, so what did I say wrong? I actually repeated what you said. What's less dense? Tell me again. What do you see here? The parcel's over here, right? This is the parcel. So the parcel's what compared to the environment? Julian?
It would it be more dense?
Well, I did say that the originally I said the parcel's colder. Does this look like the parcel, which is here, is colder than the air around it?
No.
It's warmer.
Warmer.
So the parcel's warmer than the air around it. Therefore, it's
Less dense.
right. Okay. So in this case, the parcel is warmer than the air around it, which would make the parcel what? If it's less dense.
Would it be saturated?
Not necessarily.
Is it warmer?
Aaron, what are you saying?
It's S. T. If the parcel's, she says it's stable.
If the parcel's warmer than the air around it, you still saying it's stable?
Is that what you're saying?
Is that a yes or a no?
Unsure.
The parcel's unstable here, right? Look. Here, pay attention, everybody. This parcel because the blue lines represent the parcel. The parcel, any place along it, is going to be warmer than over here, isn't it? This is to the right is warmer, left is colder. So the parcel is warmer, therefore the parcel is less dense than the air around it, and we say that the parcel would be unstable. What's another word we could have used? Sam?
Stable.
No, it's unstable. What's another word we could have used
Oh,
other than unstable?
it's accelerating because unstable.
Yeah, but another word?
Be buoyant.
Couldn't we have said buoyant? Buoyant means unstable. Again, and those are these kind of things I want you to say over and over again, because the more that you use it, the better it becomes. Right? You don't learn new vocabulary until you use it. You got to know that you know it.
So this would be like the reasoning behind like why heat likes to rise is because it's more buoyant than the air around it.
Okay, so yeah, see, and this, Zach, this is what drives me crazy, because does heat rise? And the answer is no, that doesn't make any sense. What rises? What is the thing doing the rising? Air. Air in a balloon or a parcel will rise by itself if it is warmer than the air on the outside, because if it's warmer at the same pressure, it's less dense, and less dense things rise. So to say that heat rises is not true. Warm air rises if it's warmer than the air surrounding it, assuming it's at the same pressure.
So like if you're boiling a pot of water, that's like water vapor that's coming off, or it would be liquid, like the cloud that would.
Yeah, and so what happens is you've got liquid turning into vapor. Now that vapor comes into the air and it's warm. It's 212 degrees Fahrenheit. So that air will then rise by itself.
Okay.
And that's why the steam rises, because it really recondenses. But the idea is that it's going up. It's warmer and buoyant than the air around it. Now, in reality, does the warmer just go rising all the way through the roof? What happens is it starts to mix up with the air around it. And therefore, when you just boil water, it's not truly a parcel theory anymore, because we say that a parcel doesn't mix. And in real life, air mixes. But yes, that's what it is. So one of the things that as a teacher of science, I want to make people smart. And being smart means you explain things that make sense. We take the simple heat rises, which is not a true statement, and we say, what's really happening, right? Does that make more sense? I mean, I hope you understand. It's not heat rising. I don't even know what heat is. Warm air rises. And that's important because we're going to deal with that a lot. So I don't mind re-emphasizing it. And so Zach, again, seeing those relationships, understanding that thing and working it through is how you learn and you're smart. And I think it's really important that you practice intelligence, because elsewise you live in a world like we live in, which is full of stupid people saying stupid things that don't even make sense to me. Right? We got to be rational. If we want to quote unquote follow the science, which is annoying, we have to learn how to speak correctly and say the right things. So in this case, does that make sense? The parcel will be warmer than the air around it. Do you agree this way is warmer? And if that's the case, being at the same pressure, this warm air will be less dense. Therefore, the parcel will be buoyant. Does that make sense to you? But we said, what's warmer than the air around it? What's warmer than the air around it?
The parcel.
Okay. Do you see on here the parcel? Do you see more than one parcel? Doesn't this blue line here, doesn't that represent the parcel? Doesn't this line here represent the parcel? This is the parcel if the parcel is dry. Lifted, dry adiabatically. Lena, how far?
Whole way.
The whole way. And this line represents the parcel if the parcel were lifted
The whole way.
wet adiabatically the whole way. Do you agree that a parcel could go up dry adiabatically for a while and then wet adiabatically? So where's the parcel going to be? Somewhere between that, and that. Does it matter? Does it matter where the parcel is in looking at that it's going to be warmer than the air around it in yellow? No matter what, the parcel, any parcel lifted from P to P minus delta P is warmer than the environment around it. Therefore, any parcel, if I lifted it and let go of it, would do what?
All right. It would rise.
How would it rise? Everybody, it would rise by itself. We'd say that the parcel is unstable. We could say the parcel is buoyant. No matter what. Hey, I'm going to the movies. Do you want to come with? Absolutely. No matter what, I'm going to the movies. That could be an answer, right? And you'd use that word, absolutely. So the question is the parcel going to be unstable with this yellow case 1? Absolutely. No matter what, wet, dry, or somewhere in the middle, it's going to be unstable. This is what we call absolute instability. It's absolutely unstable. Remember, instability is a race to get cold between the environment and the parcel. In this case 1, who's winning that race? The environment. It's getting faster than what? Any parcel. Because a parcel can only cool dry or wet adiabatically. That's it. This, where the atmosphere cools greater than 10, hardly ever happens. It happens over the lake. Doesn't happen very often. Now, what if I did this? In this case, we'll call this case 2. What's the relationship between the orange line and any of the blue lines?
Much warmer.
So how would I say, right, the environment is warmer. So what would any parcel be?
Stable.
Okay, so what's the relationship between the lapse rates?
The environment is less than the wet adiabatic lapse rate.
Right? Which is always less than the dry. Do I need to write this down? That's always the case. In this case, what would the parcel be? Zach, you said it would be stable no matter what. So what do you think we call this case?
Absolutely stable.
Right? That's absolute stability. Or we say the parcel is absolutely stable. So remember how we said the parcel can be stable or unstable. In this case, we're saying it's absolutely stable. No matter what. No matter what the parcel is. Okay. Now, what about this? What about this case? First of all, this is case 3. What is the lapse rate of the environment in case 3? In simple words.
Between the dry and wet adiabatic lapse rate.
Okay, the environment's cooling somewhere between the wet and the dry adiabatic lapse rates. How would I write that down now, Zach?
The dry adiabatic lapse rate is less than the lapse rate of the environment, which is less than the wet adiabatic lapse rate.
You just said this. Is that true? Can the dry be less than the wet? You went the other way around. Try it again.
Oh. So, yeah, the wet would be less than the dry.
Do you agree it falls in between the two? And what do we call that? Isn't that what we already said? So listen, hey, I'm going to the movies. You want to come with? By the way, just as a joke, as a side note, anybody? Whoop, hold on. Anybody have a problem with that sentence? If I said to you, I'm going to the movies, you want to come with? Does anybody have a problem? Sam, do you have a problem with that question I just asked?
Yeah.
You ask somebody in a different state, they will use, I mean, away from Chicago area, they will go, what? Do you know how weird it is for somebody on the coast to go, you want to go with? With what? But people in Chicago, if you just end the sentence like that, I'm going to the movies, you want to come with? They're fine. You don't even think about it. Say it to somebody who's not from the region, and they'd be like, what? Come with what? They'd say, do you want to go to the movie? I'm going to the movies, you want to come? Or they'd say, you want to come with me? But if you just go, you want to come with, they'll go, what? That's a Chicago, that's a Midwest thing that everybody's fine with. Like that, you're fine with. You're not supposed to end the sentence like that. So anyway, I'm going to the movies, you want to come with? Absolutely, no matter what. I want to see that movie, it's the best movie ever, I'm going to go. You might say, I'm going to the movies, you want to come with? Absolutely not, I hate that movie. I could die. You couldn't bring my dead body to the movies. I'm not going with. Absolutely not. Right? You're very adamant. But most of the time, somebody asks you the movie, what would you say? Usually you're not that adamant. When somebody else, hey, I'm going to the movies, you want to come with? What would you probably say? Well, maybe. Maybe you'd say, if I have the money, or if I'm not working, or if I like the movie, right? Then you'd say if. So when you're giving an if I do this, then I will go. If I do something else, then I will not go. An if-then statement is called a condition. That's why we call this a conditional instability. So the question is then, is the parcel stable or unstable? And the answer is, well, it depends. If the parcel is dry, then, right, the parcel goes up here and it's colder than the air around it and it's stable. If the parcel is saturated, then the parcel is warmer than the air around it and we say it is unstable. Isn't that what you said earlier, Isaac? A saturated parcel will be unstable, a dry parcel will be stable. That's what conditional instability is. You don't get instability until you get saturated. Does that make sense? Now, let's imagine this. Oops, hold on. Let's imagine this. let's imagine the parcel goes up dry adiabatically, like this, to here. That becomes the LCL. And then it goes up wet adiabatically. Is the parcel here unstable or stable? Say it, Sam.
What?
Is the parcel here stable or unstable? Julia, what do you say?
The unstable.
If the parcel, remember the parcel would be here, right? And what am I comparing it to? Temperature there in the green, right?
Mhm.
So is that parcel stable or unstable compared to the green?
Stable.
Right. So it's conditional instability. The parcel is saturated, but it's still stable. And that's because it got behind. So what would make it unstable? What if I got the LCL over here? What if I went here to the LCL? And now what's the parcel?
Unstable.
It's unstable. It's warmer than the air around it. It's unstable. Where did the parcel become unstable? What's that called?
LFC.
You got it? So a parcel can be stable or unstable, but the atmosphere can be one of three things. So write this down. The atmosphere or a layer of the atmosphere or a layer of the atmosphere can be what? What are the three options?
Absolutely unstable, absolutely stable, and conditionally unstable.
Those are the three things. It's either absolutely unstable, conditionally unstable, or absolutely stable. That's your three choices. So anytime I ask you about a layer of the atmosphere, let's say from 1 to 3 kilometers, or from 2 to 4 kilometers, or from 0 to 5 kilometers, what's the atmosphere? You have to say absolutely stable, absolutely unstable, or conditionally unstable. That's the answers that you can give me. A parcel can only be stable or unstable. I mean, you could say neutral, but whatever. But the absolute, that comes with the layer of the atmosphere. Sam, so that you have this down, right, that is what we call static stability. That's the name of it. Lena, we learned this at 11:15. I'm not going to worry about that name in this class. The question is, what's the only thing that you need to know to answer that question? What's the only thing that changes? What's the only thing that you need to know to answer the question, what's that layer of the atmosphere stability?
The environment's lapse rate.
The environment's lapse rate. If it's less than 6, then we know it's absolutely stable. If it's greater than 10, we know it's absolutely unstable. If it's between 6 and 10, for the sake of this class, we know that it's conditionally unstable. Now, look at your stuff. Look at question 4. Write down the answer, and don't say it, just write it down. What's the answer? Now say it.
It would be absolutely stable.
Absolutely stable. The parcel always cools faster than the environment. In the race to get cold, who's winning that race? The parcel, no matter what. Absolutely stable. If I wrote to you, if the parcel always cools slower than the environment, the atmosphere is said to be absolutely unstable. So how would you answer question number 3? Give it a second. Try to think of how you would put that in there. What would you say? What do you think, Isaac? What are you going to say?
Conditionally unstable.
I wouldn't put that in there. Somebody else, what do you say? Here, Isaac and everybody else, I want you to watch something here, okay? Look at this lapse rate here. Do you agree? What is the stability of this lapse rate?
It's greater than the what adiabatic lapse rate.
Well, don't forget it's less,
Oh yeah, it's less than the,
right? So that's absolutely stable. What is it here?
Conditionally unstable.
What is it here?
Absolutely unstable.
So I'm going from absolutely stable to conditionally unstable to absolutely unstable. When the line does this, what is the line doing? It's getting to be greater lapse rate. So what am I increasing? Aren't I increasing this instability of the atmosphere? The greater the lapse rate, the more unstable the atmosphere. The greater the lapse rate, the more unstable the atmosphere. What else could you have done with this sentence if I started it with this? Yeah, the question, the blank that I want you to fill in is the more unstable the atmosphere. But you see, you could have said the less stable the atmosphere. The greater the lapse rate, the less stable the atmosphere, or the more unstable. That means the same thing, doesn't it? So Sam, do you understand this is about the lapse rates of the environment?
Yes, sir.
If you went storm chasing with me, I could show you all sorts of cool ways to look at stuff. Now, in here, I'm asking you, what is the stability of the atmosphere between 4 and 6 kilometers? And what's the answer? What would you need to know? What are your possible answers?
absolutely unstable, absolutely stable, and conditionally stable.
Well, conditionally unstable, right? Just make sure there is no such thing as conditionally stable. It's conditionally unstable. That's just its name. And then what would you need to know?
The environment's lapse rate,
Between,
4 and 6 kilometers.
so tell me what that is. Everybody go ahead and do that. What is the stability? What is the environmental lapse rate between 4 and 6 kilometers?
11 degrees. Wait, no.
It's 5.5.
5.5 degrees Celsius per kilometer. Do you agree? The temperature drops by between 4 and 6, it goes from -2 to -9. That's a drop of 7.
No, it goes from 2 to -9.
Sorry, where am I going? 4 and 6. It goes from 2 to -9. That's a drop of 11 divided by 2 kilometers. That's 5.5 degrees Celsius per kilometer. What's the stability of that? 5.5 is less than 6. That means it's absolutely stable. Does that make sense? Say yes or no.
Yeah, that makes sense.
Okay. So now listen to me. When I ask you about the stability, do you understand it has nothing to do with the parcel? It has nothing to do with the parcel there. I'm just looking at the atmospheric collapse rate. That's it. The PBE and the NBE and the LFC and the EL is all about the parcel. Absolute stability, absolute instability, conditional instability, it's all about the lapse rate of the environment. So over here it says, which 1 kilometer layer is most stable? What would you look at? What would tell you that question? Or which 1 kilometer label is most unstable?
Is it going to be the one with the biggest difference in temperature?
Okay, the greater the lapse rate, the more unstable. So you're looking for the biggest drop. Which layer is most stable? The one with the smallest drop. Or in the race to get cold, what if I look at over here? What's happening between 6 and 6.5 degrees? Or 6 and 6.5 kilometers, I mean. What is this? What's occurring right here?
It's an inversion.
Isn't that an inversion? It's getting warmer. So if the race to get cold, the environment's getting warmer, isn't that stable? Isn't that really stable? It's absolutely stable. How absolutely stable? Really absolutely stable. So what's the stratosphere doing? It's getting warmer with height, right? So the stratosphere is absolutely stable, really absolutely stable. In the race to get cold, the stratosphere is getting warmer. Have I answered all the questions that I should see? Do you know how to do the rest of this lab? Is your brain hurting? How you doing, Ryan?
I'm doing my best.
Scale of 1 to 5, how well do you think you understand this lecture today? Everybody? Where are you at, Aaron?
4.
4? Okay, so what do you need to get better at it? Isaac, how are you gonna work through this? You gave me a 3.
I don't know, just keep looking over my notes. I'm not sure, look over the lectures.
So I tell you what, on a scale of 1 to 5 in trying to understand my lectures, how is the Zoom helping? How is Zoom for you? 1 to 5, give me a number.
Did you say helping?
Yeah. Like if you were sitting in class, do you think you'd get this better than online?
Yes.
Yeah.
It's a sad world we live in when we don't realize the damage we're doing to it. God, it's sad. I don't know how else to do this. I don't know what else to do. You read your book, give good lectures, but man, it's hard on Zoom, isn't it? So if you got a question, feel free to ask. This is hard. I feel bad for you. I feel bad for all of us being in this environment, but I'm not going to lower my standards. We can't afford to be dumber because for a year. So do the best you can. If you have questions, you can always email. Of course, you should ask me on Thursday. But you think you can get this lab done? Isaac, are you going to be okay? You gave yourself 3. It doesn't necessarily mean you're less than somebody else. You're evaluating yourself that way. You going to be able to do this lab? Okay. Lena, you going to be okay with it? Julia, you good? Ryan? Aaron?
Yeah.
Are you good? Sam? You can get this done? Zach?
Yeah, I think I'll be able to get this done.
Hey, Sam, when it comes to basics, man, nobody's better at this instability stuff than me. That's what I want you to be, is as good as I am at knowing how to look at a sounding and understand what's happening. Right? Storm chasers, you know what they tend to do? They learn a couple of things and they go, oh, this and this and this. Like, they don't really know it. I want you to really know it. I want you to be better than all of that. Okay, guys, you rock. I mean, I like you a lot. You did a good job trying your best today. Was it intense?
Yeah.
How you doing, Aaron?
Okay. She's doing okay.
Okay. If on Thursday, we're going to go on to something a little bit different, but this will be due before class on Thursday. So I will make the due date 12:59 p.m. on Thursday. Fair enough? And then we'll start some stuff. We'll probably get the test sometime at the end of next week. It's going to be warm for the next couple of weeks-ish. Above normal. Yay.
Yeah, I saw like it was supposed to be like 60 like next
We
week.
might get 60s on Monday. That'd be awesome. Doesn't that feel good? Ding dong. Okay, guys. Have a great week. We'll see you on Thursday.
All right,
Smile.
have a good
Thank
week.
you. Yeah, have a good week.
Bye.